I think we were talking about a lot of applications. We may want to generate some kind of probability distribution, so that maybe we can take an image and say, what's the probability that this is a picture of a cat? Or we can take some kind of cardiac data and say, what's the probability this person is about to have a heart attack? Things like that. But if you have a lot of data, we said maybe you want to parallelize things, and you have a lot of different distributions, and now you want to try to pull them together, synthesize them into one. So we need to somehow average these distributions. So abstractly, what we're trying to do is say, let's find some kind of probability measure, mu star, that's in some sense as close as possible to all the different distributions that we calculated. So argmin over all possible distributions. And then we add up the distances, weighted distances between them. So the mui's are the data that we've calculated. Okay, and we could think of this being scaled so that it's a convex combination of these things. Okay, so we said, what if we just do the easiest thing in the world? The easiest thing in the world would be like an L2 squared distance, and it gives us the easiest kind of average you could think of is just sort of a straight arithmetic type average, which may be what you want, or it may not be. You know, if you have, we said last time, if you have one here and one here, this is your mu1 and this is your mu2, then a straight average will put some weight here and some weight here, which might be what you want, or it might not be. I mean, it's possible that, you know, your data's come from different places, and the data that you used to generate this was shifted a little bit from the data you used to generate this. Maybe all of this data was data that was generated in the daytime, and all this was data generated in the nighttime, and they were naturally shifted. And what kind of average do you want? It says overall, you know, barring that information, do you want this bimodal thing, or do you want something that's really just says, this is basically what is going on, and you know, we've got some tail out here. Shifts things around. So L2 maybe is natural, maybe is not natural. You know, we want results probably that are insensitive to noise or insensitive to anomalies, which certainly L2 is not. So again, Wasserstein may be very natural here, especially since we're already actually working with probability distributions. Wasserstein is actually a metric on probability distributions. So it makes sense to think about this. So this is the problem of computing Wasserstein Barycentres. So let's focus on this problem of these barycentres. Okay, and we want to compute all of this. Same thing that we had before. And this time, instead of an arbitrary distance, I'm going to put W2 squared. I guess I'm still adding. So lambda I, and then W2 squared distance between mu I and mu. I'll say that a lot of what I'm going to do today, or a good resource, is from a paper on this by Marshall Leguet and Guillaume Carlier, which is also posted on Canvas. It's on, I forget the exact title, something to do with Wasserstein Barycentres. So what I want to do is just a few examples, really, to try to figure out what kind of distributions are we actually going to end up with when we compute these barycentres. So let's start simple. Simple is 1D. Okay, and I'm going to assume that I have a bunch of distributions that are all the same but just shifted. And we're going to figure out what the barycentre of these is. So let's suppose that I have a bunch of these things. They have a density, and they're all of the form f naught of x minus some shift. So I have this, and this, and this. Okay, and we know if we did an L2 kind of barycenter, then we would get something that was kind of bumpy. But let's try to find out what Wasserstein does for us here. So what is the thing that I'm trying to come up with? The thing I'm trying to come up with is another probability density function. All right, let's try to find the barycenter f of x. Okay, 1D has the advantage that there's exact formulas for some of these things. I think we talked about that in the first week or two of class, that we can write down an exact formula. So what do I need to do here? I'm computing Wasserstein between f, the thing that I don't know, and each one of these guys. So I'm going to say, let's suppose I know what f is. I could figure out what the optimal map is between f and fi, and I have a formula for it. Okay, the formula involves these cumulative distribution functions. Okay, so let's use these guys. Okay, so capital F is going to be, I'm not going to put a 0 there. Do this. Okay, and then my fi. This is going to be fi of t. Okay, and if we think about what this is a little bit, this is f naught of t minus ai. Okay, so this is really, if I take my reference density f naught, this is like the cumulative distribution for my reference thing, but it's shifted. So I could think of this as f naught of x minus ai. Okay, so let's let Ti be the optimal map from Fi to F. And we should be able to start computing explicitly what the Wasserstein distances are that show up in this barycenter problem. Okay, so remember the condition was the amount of mass to the left of x in my source is equal to the amount of mass to the left of t of x in my target. Okay, so the optimal maps are Ti of x equals capital F inverse of Fi of x. Which is capital F inverse of F naught x minus ai. Okay, so then I can write down explicitly what these distances are. So this is the thing that we want to minimize. The beast we want to minimize is the sum lambda I W2 squared. This was the map from Fi to F. So we're going to be integrating over R of x minus Ti squared. times fi. Okay, and conveniently, I can put this all in terms of my reference distribution because we started with a simple problem. Okay, so let's say we got our lambda i's. Okay, ti of x, we computed here. That's this guy. So x minus f inverse f naught x minus ai times f naught of x minus ai. Okay, and just to make things a little cleaner, okay, I'm integrating over r. I have an x minus ai. I can just do a change of variables and shift things over a little bit. And I'm still integrating over r. So this just becomes, the x plus ai comes out here. Minus f inverse of f naught of x, f naught of x. This is composition. This is a subscript. Okay, this is the thing I want to minimize. So what's the object that I'm trying to choose to minimize this? What do I have freedom to change in here? What's that? Lambda I. So lambda I is actually fixed in the problem, so I don't get to change that. The what? The shift. The shift is also given to me in the problem. So remember, these are my data. So you've gone out, parallelized things, and whatever, you've come back with these different distributions. I don't get to do anything about these. What I'm trying to do is find an f that's as close as possible to these. You look like you want to say something.
No.
You don't want to say something. Okay.
You get to pick your representation of f, so f inverse and f, right? That's what you get to shift.
That's what I get to pick, f inverse of f naught here, right? So lambda I is data. It might just be they're all equally weighted, or it might be that one of the clusters, one of the nodes got more data than others, so I gave it more weight. I don't know. So those are given to me. The shifts are just telling me how much each of these distributions that was given to me was shifted. What I'm trying to solve for is this. Okay, at the end of the day, what I'm trying to solve for is this little f, which right now I'm representing in terms of capital F. Or, as has been suggested, really, if I could find this whole beast, I'd be in business. So instead of just trying to solve for capital F right now, I'm going to let this whole function be my unknown. So let's write this. G of x equals f inverse of f naught of x. And what's our goal? Our goal is, let's find capital G to minimize. Okay, this sum. X plus ai minus g of x squared. Okay, and then when we minimize it, we better come back and check at the end of the day that when we undo all of this and solve for f, we actually do get a probability density. Okay, so how do I minimize something like this? More or less take a derivative, yeah. I could take the first variation of this thing, right? I'm solving for a function. Okay, so let's try to compute the first variation. Let's see, I don't know how much detail you want in this. The easiest way to think through it is always to say, let's look at g plus epsilon times h. And we want to have a minimum when epsilon is equal to 0. Right? So we take the derivative with respect to epsilon and set it equal to 0. So if I do that, what do I get? That 2 is going to come down. Lambda I, I'm still integrating. So the 2 came down. I have an x plus ai minus g of x. Okay, minus epsilon times h, but I'm going to take epsilon to 0. Okay, and then derivative with respect to epsilon means I pull out a minus h. So what I really want is for this to be equal to 0 for all possible choices of this function h. Say for all c infinity h. What's that? I lost my f naught. Thank you. Okay, and now we make a usual argument, right? This is true for all functions h, which means that this part of the integrand here should be 0. In particular, we're multiplying my f naught here, so on the support of f naught, this term here should be 0. So I should be able to conclude that on the support of f naught, we have x. Oh, sorry, let's keep the sum out here. X plus ai minus g of x is equal to 0. Okay, now I'm in business. Now I can solve for my g of x. All right, so what's going on here? I have, if I assume the lambda sum to 1, they don't have to, but you can always scale things so that they do. Then what do I have? I have g of x is equal to or alternatively, in the lambda sum to 1, x plus some kind of average shift. Am I missing an n somewhere?
Yeah, I mean, that sum runs over g as well, but it's independent of I, right? So don't you get gn?
The lambda sum to 1.
The lambda sum to 1.
Oh, the okay, never mind.
Yeah, and I got the g is independent of I just because I used this trick where I put everything in terms of my reference f naught. Okay, so we got a g. We found something to minimize this, and the question is, can we back out of it an actual density function that would somehow minimize this weighted sum of Wasserstein squareds? So I need to go back to what g is. G is f inverse of f naught. Okay, so we have f inverse of f naught of x is equal to this function here. All right, I know what f naught is. What I care about is this capital F. So I guess the obvious thing to do here is apply capital F to both sides and get rid of this inverse. So I have capital F of x plus this weighted shift is equal to capital F naught. Can I solve for capital F? You're nodding. I just need to do a substitution. Good. I just wanted to see if you're awake. That really is just a calculus 1 question. So yes, I relabel things. And I can indeed get the cumulative distribution function for my unknown density. And this looks really familiar. It's the cumulative distribution function of my reference evaluated at x minus a shift, which we've seen before, x minus a shift. So we already know what density this comes from. So this is indeed the cumulative distribution function for f of x equals my reference where I've applied some kind of average shift to it now. Okay, so what does that mean? If these were my, F1, F2, F3, they're all shifted by a different amount. I'm not gonna, when I do my barycenter, I come up with a new distribution. It's not gonna be all silly and bumpy and have multiple modes like an L2 barycenter would. It's gonna have exactly the same shape of this, but now it's gonna be centered at the average shift. They're all shifted by a different amount. It's gonna average the shift. So we're gonna be maybe a little to the left, maybe over here somewhere. In other words, the same density, but undergoing the average shift.
What was the point in using cumulative distribution functions?
What was the point in using cumulative distribution functions? The point was, so along the way here, I have to compute what I've erased. I had to compute the Wasserstein metric, right? So I was trying to minimize this weighted sum of Wasserstein metrics between Fi and F being the unknown. So in order to compute the Wasserstein metric, I need to solve an optimal transport problem, right? The cumulative distribution, in one dimension, there's an exact formula for the solution of the optimal transport problem, and it involves these cumulative distribution functions. In 2 dimensions and 3 dimensions, this doesn't work. In 1 dimension, I can write down the exact formula, and it let me write down exactly what this optimal map was. Right? If you just give me a bunch of distributions or multiple distributions in 2D and say write down the optimal map, I'm going to say, unless these are really simple, I cannot do it. In 1D, if you give me 2 densities and say write down the optimal map between them, I can always do it. And it was in terms of these cumulative distribution functions, which, by the way, is the hint for the next homework problem. Right? It's in 1D, you can use this to compute the Wasserstein metric. So this is kind of natural, right? If We go out and compute a bunch of probability distributions. Then when we average them, we're going to get an average that somehow shares the same structure as all of these things. It's going to carry the same shape, which makes sense in a lot of problems. You know, if we're computing a bunch of Gaussians, but they've been shifted for various reasons, it's probably reasonable to assume that the aggregate, the summary of them, should be some kind of Gaussian. And in 1D, at least, that's what's guaranteed to be the case. This is just kind of an observation. If you look at F and where it gets mapped to, so it might get mapped to, say, this is T1 inverse, T2 inverse, T3 inverse. If you add up all of these things, so what were each of these? If we just invert the map that we had before. Okay, we undo the average shift and then we shift it over to the ith position. If you add all of these up, they actually sum to x. So on average, somehow this thing is not moving. This is actually a sufficient condition for optimality. So if you're trying, not just in one dimension, but in higher dimensions, if you're trying to compute the Wasserstein Barycentre, if you come up with the distribution, you find what it maps to into all your given distributions, and you add them up, and you say, oh, at the end of the day, it's just the identity, then you know you've actually got the barycentre in your hand. This is a sufficient condition. So this is a sufficient condition. For F to be the barycentre. Which is also true in higher dimensions, and it doesn't assume that all these shapes are the same. It's also true in Rn. I'm not going to go through the proof of it. It's in the paper that I mentioned, and they use a duality type of result to build up a lot of this theory. Any other questions on that example? Okay, let's do another special case. Okay, so we'll move out of one dimensions, but I'm going to simplify in another direction, and we're just going to take two measures, but they don't have to look the same. So let's take the barycentre of two different measures, mu1 and mu2. Okay, so let's just draw a picture. Maybe this is my mu1. And maybe this is my mu2, supported on a triangle or something. So they don't have to look the same anymore. And now the question is, what is the average of these two measures? Okay, so I'm going to make a claim. First of all, if we're given these two, then we should be able to compute an optimal map between them. So let's let T be the optimal map between these guys. So let's let T which pushes forward mu1 to mu2 be optimal. Now, if we were doing an L2 squared barycenter, again, what we would get, we'd get kind of a pale circle here plus a pale triangle over here. I would try to have both of them in place and nothing in between. And now what I want to claim is that if we do Wasserstein, that's not the case. What's going to happen is that this is going to travel and also morph. So it will be some sort of combination of this circle and triangle, but also it will be shifted over to be sitting in the middle of them. So can we write down a map that does that? Well, this is going to be my claim, that the Wasserstein barycenter is, and here we're going to look at a map, and a sort of average map between the identity, which stays here, and T of x, which goes over here. We're going to look at an average map that maps in between, and then see what the push forward of this is under that map. So I claim that we're going to get this result. So lambda 1 times the identity plus lambda 2 times t push forward mu1. All right, so it says, okay, the optimal map from here goes to here. Well, instead of going all the way there, we're going to go partly just leave it here, partly go there, so we're going to end up here. We're partly going to leave this on the circle and partly going to try to shift it to the triangle, so the shape changes a little bit, the location changes a little bit, and we get something in the middle here. Okay, but let's check and see if this is what we really get. This is just a guess. Okay, so let's let's start with a more arbitrary measure. Okay, so let me draw a diagram again. This is my mu1. This is my mu2. And I'm going to have something out here. Right, and we're trying to find the measure mu that's going to minimize this weighted sum of the Wassersteins. Okay, so this, again, this map was T. We want to try to find mu to minimize lambda 1 times W2 squared mu1 and lambda 2 W2 squared mu2. Okay, so in order to do this, okay, I'm going to keep working with the Mosh problem where I assume I have maps here, just for simplicity. I need a map from here to here. I need a map from here to here. This is a comma. There we go. So let's call this T1 and this T2. Okay, so let Ti push forward mu I into this in-between thing. And these are optimal. Now I want to try to, again, minimize this. So I'm going to try to make an observation. I drew this measure out here. Now we have some sense, probably some intuition, that the guy that minimizes this distance shouldn't be out here. It should live in some sense in between these two things, whatever that means. Right? But it doesn't make sense to go this way and then also go that way. So I'm going to use that idea. I'm going to decompose this map T1 into two pieces. And one piece is going to go in the direction of T, and one piece is going to go orthogonal to it. Yeah, you could think of it as a projection. I'm gonna take this map. Okay, and this is pointwise. So for a given point x, I compute T1 of x, and then I say, now I projected us onto the direction of T, right? Because of course this area at each point x could point in different directions. Okay, and then I have whatever is left. So whatever is left, I'm gonna call S1, and I'm gonna do the same thing here. I'm gonna take my map T2, project it into this direction, and then take whatever's left. Whatever's left is orthogonal. Okay, so that's the way to write this. So T1 of x, this optimal map, has a piece that goes in this direction. So it starts at x. It moves in the direction of T of x minus x. It starts at x. It has one component that moves in the direction of T of x minus x with some weight, right? Because we're not going all the way out here. It's going part of the way, and I'm not sure how far. But this is a way of representing this projection here. And then I have whatever is left. And now whatever's left is going to be orthogonal to T minus x. So this dotted by T minus x should be equal to 0. Is that okay? Okay, and then I'm going to do the same thing with this other guy. So T2 is x plus. Now I'm going in the opposite direction. So I'm going actually in the T inverse direction. Right? The map from here to here is T inverse. So C2 of x, T inverse of x minus x, plus S2 of x. Yes?
Is that your product
So this is just a normal Euclidean dot product. This I'm expecting to be true pointwise. So for any fixed x, this is just a vector, a constant vector, and this is a constant vector. And I expect them to literally be at right angles to each other. But yes, good question. It matters, obviously. Okay, now with this decomposition, let's try to look at what this thing does. So the beast that I want to minimize is lambda 1 okay, Wasserstein squared between mu and mu1. Okay, so I have to look at x minus t1. So x minus t1, that leaves me with c1 of x, t minus x, plus s1 squared. And then weighted by the amount of mass that I'm moving. Okay, plus the other guy. So C2 of x, T inverse minus x plus S2 d mu 2. Okay, what's the effect of say S1 on this value? Can you look at it and tell me what value of S1 would make this as small as possible? 0. Why?
You don't want to go up. You want to go across to mu 2.
Yeah, so that's intuitive. I don't want to go up. I want to go across. Looking in here, if I multiply this out, all right, I'm going to spoil this. Okay, I get this term, which I can't do anything really about, plus S1 squared, which is certainly positive when I integrate it, plus the dot product between these two things, which is 0. So all S1 does is make this value bigger, right? Any non-zero S makes this go up, because it's just adding a component in this direction. S2, same deal, right? You know, we're just doing like the Pythagorean theorem here, basically. That we've got this distance squared plus this distance squared. There's no dot product, so this guy is just increasing the value. So these are certainly minimized for S1 and S2 equal to 0. I feel like I'm in a vector calculus class with people trying to, let's see, right hand rule, and then there's always, during a test, there's always somebody sitting there with their left hand trying to do the right hand rule, and you feel sorry for them. Okay, so, okay, wherever this distribution is, right? If we look for an optimal map from here to here, if we can express that in terms of my original optimal map T, that's good. And if I take this and shift it orthogonal to that, I'm always going to make the value go up. So in other words, I want to take this and do what we intuitively thought we should and stick this in the middle somehow. Okay, so we're down to this. We want T1 to have this form, and T2 to have this form. What other conditions do I have to work with that I could use to sort of simplify things or to get more information? T is optimal, yeah. That's important. What else? T is feasible. That's important. So on that note, what's the relationship between T1 and T2?
They're scalars of each other.
They're scalars of each other? Kind of. So T1 goes from here to here. T2 goes from here to here, right?
Wait, didn't we get rid of the S though?
We got rid of the S, yeah. So by here, I mean here.
Right, so right there.
They should end us up at the same place, right? So I've written down two maps here, and it's not at all clear that they should end us up at the same place from the way I've written it here. But they better, right? T1 should take mu1 and push it forward into mu. T2 should take mu2 and push it forward into exactly the same mu, Right, and I can write down that condition. So we certainly require these conditions to be the same. Another way that I'm going to write it that's going to end up being useful. Right, if I go from here directly to here, I get mu. If I go from here to here to here, I should also get mu. Right, so here I travel along T inverse, and then I travel along T1, I get mu. Or I travel along T2, I also get mu. I should get to the same place. So this is basically equivalent. T1 of T inverse should do the same thing. Okay, so let's write down T1 of T inverse. We know what T1 is. Okay, so let's write down T1 of T inverse and see how it compares to T2. T1 of T inverse is going to be a T inverse plus a C1 of T inverse. T of T inverse is X minus T inverse. So what do I have? I have some part that's trying to go in the X direction and some part that's trying to go in the T inverse direction. Yes? Oops. Okay, so let's write it explicitly like that. That times X plus 1 minus C1 of T inverse times T inverse. Okay, so that's T1 of T inverse. On the other hand, we said T2 should do the same thing. So T2 is here. T2 is also written as a combination of X and T inverse of X. So if I break it up in the same way, I have 1 minus C2 of X times X plus C2 of X times T inverse of X. So what do we expect? What did we learn? So we expect them to be the same, exactly, right? On the one hand, we're going here to here. On the other hand, we're going here to here. We should end up at the same place. So what do we expect? We expect that C1 of T inverse of X plus C2 of X is equal to 1. Okay, that was using, I guess, feasibility. Then we need to use optimality. I don't remember who suggested it, but of course we need to use it. Okay, so let's use this, and let's now try to minimize the thing that we started with. Lambda 1, W2 squared, mu 1, plus lambda 2, W2 squared, mu 2. Start on a new board, give myself a little space. Let's see, are we done with this picture? I think we're done with this picture. Okay, so what do we have? We have lambda 1.
Which is which over there?
Which is which? What do you mean which is which?
Mu.
Mu and mu 1.
And then you should have mu 1 over there.
And then mu and mu 2.
Oh,
So this
okay.
is a comma.
Okay.
And this is a comma, and this is a 1.
Thanks.
Okay, lambda 1 times a Wasserstein metric. So that means we have to do an integral. All right, we're looking at the optimal map from mu to mu 1. All right, so that was, we're going to have an x minus t1 of x. So this is the stuff that's left. So c1 of x, which is going to get squared. T of x minus x, which is going to get squared. And the amount of mass that's getting moved. Plus lambda 2. We have another integral. Now we're going from mu to mu 2. So we're going to use this map. We have a c2 of x. It's going to get squared. But c2 we can put in terms of c1. So we have a 1 minus c1 of t inverse squared times t of x minus x, t inverse of x minus x. And the amount of mass that's being moved. Okay, so not the first time today that we've looked at an integral that we want to minimize, and our goal is to find a function. What's our unknown function that we're trying to solve for now? What's that? T. So T is the optimal map from mu1 to mu2. Right? That's part of the data, basically. We're trying to find this barycenter mu, right?
So C1.
C1 is the thing that's going to tell us where mu lives. Now, this is uglier than the integral that we tried to minimize before, because here I have c1 of x. Here I have c1 of t inverse of x. Also, I'm integrating against different measures, which is kind of inconvenient. Am I stuck integrating against different measures?
No.
Nope, what can I do?
Can you switch them both to mu or something?
I could switch them both to mu, or I could switch them to mu1. Right? I happen to know that t is the optimal map from mu1 to mu2. So I can use t to move between those two. All right, so let's say I want to go from mu2 back to mu1. I need to substitute for t inverse. Okay, so let's substitute for t inverse in the second integral. Okay, and now what do I have? First integral stays the same. Okay, I have 1 minus C1. I'm substituting for T inverse. So now this is just something simple that goes in here. I'm substituting for T inverse. Substituting for T inverse, so this becomes a T. And T inverse has taken us from mu2 back to mu1. So I'm integrating against mu1 now. And now I'm in business. This is something that I can try to minimize. Okay, so we do what we did before. Take the first variation. And what do I get? I get a 2. I'm going to take, I guess, everything inside one integral now. So I get a C1 of x. T of x minus x squared is through everything. Here's a lambda 1 plus a lambda 2. C1 of x minus 1. I have an x minus t of x squared through everything. I have an h of x. And I have a d mu 1. And this should be equal to 0, again, for all functions h.
Why is HC 0?
It can be C0 or C infinity, it doesn't matter. All right, now this is easy to solve for C1. Lambda 1 plus lambda 2 is equal to 1. So what do I get? I get C1 of x minus lambda 2 is equal to 0. So C1 of x is lambda 2, and C2 of x is 1 minus lambda 2, which was lambda 1.
So you're just taking the convex combination between the...
It's just taking a convex combination, yeah. So what did we learn? We learned what T1 is. Right now I've got everything in place to characterize T1, to characterize T2. Here's T1. So now we know that T1 of x is equal to x plus C1 that's lambda 2, T of x minus x. Another way to write this would be lambda 1 x plus lambda 2 t of x. And why is that important? That's important because T1 tells me what mu is. Right? All along, mu is the thing that we didn't know. We just said, suppose we have mu. We write down these maps. This is what happens. What's the way of coming up with a map that would minimize this whole thing? But the whole thing we were trying to solve for was mu. So now, okay, if I draw my picture again, here's my mu1. Here's my mu2. And now I've come up with this map, T1. So now if I take my source and I say, okay, what's its image? What's its push forward under T1? I get something, whatever it is. And this is going to be my mu. So at the end of the day, we're going to say the mu that minimized all of this the mu that minimized all of this, is nothing but the push forward of mu1 under this map, under this averaged map. Okay, so this is the way of expressing the barycenter. Yes. Do I have a one-parameter family of barycenters? You mean in terms of the lambdas?
Yeah.
Yes, absolutely. So as you change the weights, if you take lambda 1 equal to 1 and lambda 2 equal to 0, you'll get this one. If you switch it, you get this one. And as you vary it, yes, you get this family that morphs into here.
So you choose a lambda before you actually compute
You choose a lambda before you actually compute it. So you might weight them equally. You might say, I used a lot more data to come up with mu1 than to come up with mu2, so I want to assign more weight to it. Maybe I give it a 2/3 weight, or whatever. Or I mean, maybe you're trying to do some kind of image morphing, and you actually want this family, and to let this walk along here. Okay, so it's another simple example, but you get hopefully some intuition into what these barycenters compute. They're very different from the L2 barycenters, from just a straight average, but in some problems you can imagine this would be the natural thing that you certainly want to say. One more example. I'm not going to do all the details of this, but I'll give you some of the highlights. And again, the details are in the paper that I mentioned. Okay, now we're going in multiple dimensions, whatever dimension you want, however many profiles you want, but they're all Gaussians. So what is the barycenter of Gaussians? Okay, and again, if you take an L2 type barycenter of Gaussians, it is certainly not a Gaussian, right? It's going to have, you're going to get this sort of multimodal thing. But here I claim it is indeed a Gaussian, which again, it's natural. This is probably what you want in a lot of problems, that, okay, maybe the Gaussians were shifted for various reasons, but overall things seem like they want to come from a Gaussian. Okay, so this is the sort of highlight summary. Let's let Fi be a Gaussian. So it's going to be, okay, we rescale things properly. Okay, so each of these Gaussians is characterized by this symmetric positive definite matrix. So for I, positive definite and symmetric. Okay, so what we're going to claim is that the barycenter has the form also of a Gaussian for an appropriate choice of matrix here. And the strategy is going to be to verify this sufficient condition that I wrote down before, that if you look at all these optimal maps, on average, they don't go anywhere. Okay, so we certainly need optimal maps from each fi to f. I'll go the other way, f to fi. What does the optimal map between two Gaussians look like? Do you know? A shift and a morph. Okay, yeah. Can you? That generalized what we just did. Okay. So it's a particularly simple kind of morph. Well, so when we're doing the morph, we're not trying to change a circle into a triangle in the case of Gaussians, right?
You're changing the variance?
We're changing the variance, but what am I doing? I'm really just stretching it or squishing it, right? This is just linear. So this is my claim, first of all, that if we want to come up with the optimal map between Gaussians, it's actually just a linear mapping. So I claim this map is linear. Ti of x has the form Ci times x, where Ci is symmetric and positive definite. Okay, if I can find a measure-preserving map that has this form, then I'm done. It's certainly optimal, because this is the gradient of a convex function, yes? So this satisfies the optimality condition right off the bat. So the only question is it feasible? So for mass conservation, what do I need? Then I require that g of Ci of x, I'm not working with g here, calling this fi of Cix times the determinant of Ci is equal to f of x. Okay, so what do I really need? I have, there's my fi. It's square root of determinant ai. I have this determinant ci times exponential of minus, now x transpose ci transpose ai Cix should be equal to the root of determinant a times exponential of minus x transpose ax. Okay, so what do I really need? I need to find a matrix Ci such that this matrix here agrees with this matrix A here. So Ci transpose Ai Ci is equal to A. Okay, and this is my claim, is that we can do this. So I'm just going to put the easiest way to check something is true is if you can write down an explicit solution. So let's write one down. This guy works. AI to the minus a half. So I'm working with positive definite matrices here. I can do this. AI to the 1/2, AI to the 1/2, to the 1/2, AI to the minus 1/2. This is symmetric, right? This is positive definite. And if we run this in here, we're going to get a lot of cancellation happening. And it does indeed, it should indeed settle down to the matrix A. Any intuition?
Having lots of time on your hands?
Having lots of time on your hands, yeah. So yeah, I think that's part of the answer. It's called playing with combinations of things until you find one that works. And knowing that it has to have this sort of symmetric structure, certainly. Okay, so this is the optimal map. We have the optimal map. So Ti of x is Ci times x is optimal. And this is useful to know that Gaussians to Gaussians, you can always write down optimal maps. It's equivalent to taking an ellipse and morphing it onto an ellipse. These kind of linear maps. Okay, it's a linear map. Okay, and then secondly, we know that a sufficient condition for optimality is that lambda I Ci is equal to the identity. Okay, so it comes down to, and I'm not going to go through the details of this. You can look in the paper if you want. I'll tell you the highlights. It comes down to just need to show that this matrix equation, so lambda I, all of this, AI minus 1/2, AI 1/2, AI 1/2, 1/2, AI minus 1/2 equals I. This matrix equation has a solution, and here the unknown is A. A characterizes the barycenter, right? AIs were the data from our given Gaussians. So we need to show that this has a solution A that is symmetric, positive definite. The argument was based on a fixed point argument that they used in this paper. So this was showed via a Brouwer's fixed point theorem. Okay, so again, not going into the details, they set this up. They show that, you have some space of matrices mapping into itself, and you sort of satisfy your conditions. There has to be a fixed point so they get a solution. If you get a solution to this, then automatically this is a sufficient condition for optimality. This is nothing but saying that we have this barycenter F characterized by A, and you look at the various maps to it. On average, the maps don't go anywhere. That's the condition for optimality. But what's the really key takeaway of this? That I said it at the beginning, the barycenter of Gaussians is, again, a Gaussian. And that's the important take-home message, that this process of doing Wasserstein Barycentres somehow preserves a lot of structure in your underlying problems. You know, you had right off, you get the barycenter right off, you could read off important things like mean and variance from it, and know the structure of it. And this is something that you'd certainly want in a lot of problems. So these are techniques that are used in machine learning, for example, where this is the big problem, is let's come up with this, aggregate these probability distributions. And these are some of the reasons why this is a good tool, because these barycentres, these averaged measures, have nice structure. Any questions on that? I'm going to leave that there. Next class, I want to move on to another application that I like in geometric optics, where the problem is designing lenses and mirrors to try to reshape beams of light. But that's it for today.